Okay, so welcome to a new chapter. This is chapter 5, section 1. We're going to be talking about area. So before, when you talked about area, it was probably talking about it in terms of geometry, right? You have something like a triangle or a square, or a rectangle, I should say. You have a length and a width. You have a height and you have a base. You could talk about the area of these shapes, right? Area equals half base times height. Area equals length times width. And that's all. That's nice, but what we want to do is we want to take this idea that we have from geometry and put it into calculus. Put it into these sort of situations where instead of having nice geometric shapes, we're going to have some sort of function and some interval and say this terminology of area under a curve. So we want to start thinking, is there some just basic curves that we can use geometry to somehow find their area? For example, if you take the function y is equal to 1 everywhere, what does that look like? Well, it looks like you have this line. And so if, say, on the interval 1, 3, I want to know what this area is, that is the area that if I have my x value 1, x value 3, and I draw the area sort of bounded in between the curve y equals 1 and the x-axis, I get this area. So can I find that area? And well, that's a rectangle, so I sure hope so. So we had length times width. So the length of 2, or I'll say a width of 2, and a length of, how high is it? 1 unit. So the area is 2. Okay, so that's straightforward enough. We have a rectangle, we use the same methods. Okay, so let's take another shape. So how about y equals 2x? This is just a line at an x value of 1, your y value is 2, and you extend this line going out in both directions. Can we find the area bounded in between 0 and 1? So that is between x value 0, x value 1, this area. Well, that's just a triangle. And its base is going to be this, so that's 1, and its height is 2. So my area here is going to be half, and then base times height, or just 1. Still, that's straightforward enough. Let's change this problem slightly. After I erase everything. Instead of doing 2x, let's do x plus 1. What does this curve look like? Well, at a y value of 1, you have your intercept, and then y of 2, with an x value of 1, you have your point, and you draw the line connecting those two. And we want this area. Well, now it's not really a shape that we really talked about. But we can sort of do this problem of breaking it into smaller pieces. And that's one of the things in math we like to do a lot, is break into smaller pieces. And then do each piece individually. I can break it into, right, a triangle, this one up here, and then a rectangle, this one down here. Okay. And we can find each area individually. The area of the triangle itself would be half times the base. Well, the base is this, so that's 1, times the height is 1, because it's going from 1 to 2. Okay, and then we have the area of the rectangle we have. Well, it's a 1 by 1 rectangle, just looking at what the y-coordinate of this point is versus the y-coordinate of this point. So that's 1 times 1. And as you might guess, so we have these two things that they're not overlapping. The triangle and the rectangle are not overlapping. And we want the total area. So total, you want to think sum. We're adding them together. What does that give us? 1/2 plus 1, or 3/2. So we were able to break up this area into these smaller pieces and add them together. Okay, so it seems that maybe if we could break in the smaller pieces, that might help with us computing area. Now there's a problem that sort of glossed over so far. If you look at the sides of these shapes, you have just straight lines, right? Similarly, with the problems I looked at so far, they're defined by lines. What about if you have something like a parabola? That is not a straight line. And if I want to find an area under the curve, well, now I'm stuck. I can't really use just the basic geometric shapes. So some people came up with this idea of, well, I can't use what I know to get the exact area. So instead, why don't I just approximate it? Try to get as close as I can. And you might think, well, how are we going to approximate it? Well, what we're going to do, and I'll draw this in a different color, draw in purple, is we're going to use rectangles because we know how to compute the area of a rectangle. And we can overestimate or underestimate these rectangles to give us something that's probably going to be close to what the true area is. Okay, so I'm mentioning using rectangles to approximate. Let's look at that in practice to sort of illustrate how we're going to do that. So the function that we had right there was f of x equals x squared. And if we draw a bigger picture, if we're doing on the interval from, let's just start with, well, instead of 0 to 1, just to make our picture, so we're going to start from 1 to 2. So height here is 1, and at 2, our height is 4. Okay, so we want to get this area. Definitely not something that I would look at and be like, that's a geometric shape, I know. So we want to use, like I said, rectangles to approximate. But the way so if we're going to use rectangles to approximate, the first thing we need to do is know how many rectangles we want to use. So a lot of times in these problems, I'll put n equals, and that will tell you how many you need. So let's just start with 3. 3 rectangles. So how I'm going to do this is I'm going to split up those 3 rectangles, I'm going to split up my interval into 3 pieces, 3 equal pieces. So if I split it up into 3 equal pieces, I could say, well, what's the length of each piece? And I'll call that delta x, just for notation that we'll use later. And that will be the length of the interval, so 2 minus 1, over how many rectangles we have, 3. So my length of these intervals is 1/3. So I could write out what this little part is. If I just look at this part, that is from 1 to 4/3, right? Because I want it to have a length of 1/3. And then 4/3 to 5/3. I'm just adding 1/3 each time. 5/3 to 2. Okay. So that gives me these intervals that I'm going to be looking at for creating these rectangles. Now, the easiest way to approach this is to say, well, I can either make the rectangles that on each of these intervals uses the left endpoint for its height, or the right endpoint for its height. And which one do I want to use? Well, it depends which approximation I want to use. We're going to call these, if I use the left endpoint, I'll call them left sums. And if I use the right endpoint, I'll call it right sums. To start out with, let's start with the left sums. So if I just draw this, I'll draw in blue which ones I have. See, my first one's at 1. So what is the y value? How high does it go at 1? And I'll call that the length. And then at 1/3, how high is the y value? I'll make the rectangle with the width of 1/3. So the width the same as this interval. And then this height with 5/3. If you notice, the area that I have in between is less than the total area. And that will come up in our discussion later. Okay, so we're going to call this L3 for 3 and a left sum. I'm going to have each of these rectangles is going to be, well, you have the width, 1/3, and then the height or the length is going to be, well, I used f of the left endpoint to get it, so it's f of 1 plus 1/3 f of 4/3. Plus 1/3 f of 5/3. And I could compute that number. So why don't you do that right now? Compute that number, because all we're doing is this is going to be 1/3 times 1 squared plus 1/3 times 16/9 plus 1/3 times 25/9. And as a fraction, this is 50 over 27. Or approximately 1.85. So that's the left sum. What about the right sum? How does this change? Well, my widths don't change, but now I'm picking, now instead of picking the, if I want to make it, instead of picking the left endpoints for the, to put in for the length, I'm going to pick the right endpoints. If you notice from what I've drawn in the picture, it looks like that's going to be an over approximation. So this is 4/3, and then 5/3, and 2. So you can do the computations. So do those now, and what do you get? You get 77 over 27. As opposed to before, we had 50 over 27. So notice that because one's an under approximation, as we saw visually, and one's an over approximation, they're not giving us the same number. But they're giving us numbers that aren't incredibly far off from each other. 77 over 27 is approximately 2.85. And because this one was an under approximation and this one was an over approximation, we know that if I call the true area A, it's going to lie somewhere in between those. Somewhere around 2-ish. Okay, so that is how we're going to be spending the next little bit, is just by doing this, where we're approximating the true area. And we don't have to stick with only having 3 rectangles. We could go with more rectangles. For example, we could do n equals 7. How does this change our problem? If we want to say look at a left sum. Well, our intervals aren't the same. Because now our widths are going to be 2 minus 1 over 7, or 1/7. So if we want to find the left sum, you start with 1, and then 1 plus 1/7 gives you 8/7, and then 8/7, 9/7. Adding 1/7 each time, all the way until you get to what? Until you get to 13/7 2. So then we could find what is L7. Well, L7 is going to be, we still have the width, 1/7, but then it's f of 1 plus 1/7. Look at the left endpoint, f of 8/7. Plus 1/7, f of 9/7, plus 1/7, f of 10/7, plus 1/7, f of 11/7, and we're almost there, 12/7, plus 1/7, f of 13/7. And that's a big computation, but it's only that, a computation. Notice that this computation is a lot more tedious than doing n equals 3. I will say that, as you might expect, as you increase your number of rectangles, you get a better approximation. But as you can see, sometimes this calculation can be tedious. And what if I want to, do something like L100? Well, that's going to be even more so. And using this information, you could do something like making a table. Right? You could do something like, well, here's my rectangles, number of rectangles. Here's my Ln, and here's my Rn. So, you could do 3, you could do 7, you could do higher numbers. So this was about 1.85, about 2.85, and then you could compute the other ones. Just for practice, I would suggest doing them, but you will have a check-in worksheet where you'll practice this. Just keep in mind, the more and more rectangles you add, the more tedious this will be. Now, where we're heading is, look, this looks sort of similar to what we did back in chapter 2. We have a table. And then we also know that Ln is less than A is less than Rn in this problem, right? One's overestimating and one's underestimating. So if we took a limit as n goes to infinity of Ln and Rn, they were equal, we would know what the true area is. And that was because of the squeeze theorem. So that's sort of where we're heading, is this whole taking of limits of the rectangles. So I will see you tomorrow for part 2.